Hey there, I'm Matt Jacobs, and this is Lab 2, Motion of a Falling Object. So, as for the introduction, the purpose of this lab is to examine the motion of an object falling from rest. This was done by creating one experimental model and two computational models. The experimental model is created by using Tracker to analyze the video of our lab group dropping a balled up piece of paper. Of the computational models, the first model predicts motion using gravity as the only force pulling on the balled up piece of paper, whereas the second computational model has both drag and gravity pulling on the balled up piece of paper as it is falling. The equations required for this lab are found within the Python code in GlowScript programming, or the GlowScript program, and this lab demonstrates the physics principles of Newton's second law, also known as the momentum principle. So as for our tracker data, the video was shot on an iPhone, which has 60 frames per second, and it was shot for time. T is equal to 0.583 seconds. As you can see, 54 frames of data were plotted in this graph on the right, and this shows you the height as it falls versus the time, obviously time being 0.583 seconds for it to hit the ground. For our first computational model on gravity, as you can see, the proportionality constant is equal to 0, thus making the drag force B0. And you can see here's our position versus time graph, and then here's the forces. As you can see, the only force is gravity pulling downwards. More with our code, Fnet is only W, because the B doesn't matter. It takes away all of the drag force. And you can see the ball traveled a little farther than the tracker observation with a computational model. It was 1.8 meters instead of 1.6. But besides that, the model is pretty much the same. It shows that the ball falls at a velocity that increases with gravity because there's no drag force to push up. Yeah. For our gravity and drag force, as you can see, this B constant on the bottom left changes here to 0.0016, making the drag force exist because drag force is created with this formula right here, B times ball velocity dot magnitude times J hat. So because this B isn't 0, the B now creates a drag force on the ball. Fnet is now W plus D instead of just W. And with that, because of the proportionality constant, B, being so small, there's not much drag on the system. But as you can see, there is a drag force, but it has very little effect on the motion of the system because it is so small. So here's a comparison graph showing our experimental position versus our model with drag versus without drag. As you can see, the experimental one moves the most because it was a tad different, and then the model with drag towards the end comes up a little bit as it's a little slower because of the fact that there's drag pushing against it, and the model without drag obviously is the fastest. So what does this mean? As you can see, the drag has an effect on the velocity as the velocity changes, although very, very small amounts because of the fact that there is the drag being such a small number. And so terminal velocity. So terminal velocity is reached when the force of gravity acting on an object is equal to the counter force of drag. As gravity is pulling down, drag is pushing up at the same magnitude. So therefore, terminal velocity is that final velocity that you're going to say when acceleration is equal to 0. So the velocity is constant, as in like this net force equals 0, so acceleration is 0. And then the model without drag will never have terminal velocity because there's no counter force to gravity, thus the speed will just keep increasing and increasing. And the model with drag has not yet reached terminal velocity, as you can see, because it has not changed speeds very much. So what if? What if the object was thrown downwards rather than dropped? Then the object would have released terminal velocity faster. And this is because as the speed increased at the start, the drag would increase, and therefore, as you can see in this graph, the velocity would start to slow down. And this coding right here to create this. So in conclusion, the effects of drags were evident in the results as it decreases velocity, And if we had chosen an object with more drag, like an unfolded piece of paper instead of folding it up, it would have been easier to determine the effective drag because the object would have reached terminal velocity and you could see it more clearly. Regardless, the model represents Newton's second law for an object falling from a height with the inclusion of drag force.